So does that mean if you watch a 240p YouTube video in a bigger screen or in a bigger size, will it be better, or more readable, or more understandable? Okay. Anyways, so we will continue to talk about this identical many particle, and whatever I'll teach till this Friday is part of the syllabus. That will be the last class before mid-sem, and I have to prepare the question paper on 16. So I have to kind of guess a little bit what I'll teach in 17th actually, and. This is also, I was told that you were given all the previous year question papers. So I was told to not repeat anything. So that is another challenge. So the problem is, I do not know someone who demanded this, but if I'm allowed to repeat, then the question, if I'm not allowed to repeat, then usually the question gets harder. I do not know how to do that, but let's see. I will try to make, of course, at least 50% super easy, 50 to 70% super easy. Easy means it's something that you have seen in class one way or the other, or close to the assignments. Okay, and the rest will be maybe a little 20-30% will have a little bit of twist. Huh? No, you are supposed to get, right, in libraries or somewhere they are there. That's what I was told, right? I was told that from last semester you were given all the previous year question papers. Only end sem, not mid sem.
They give not for every course, like only for specific course they give.
Okay, for my course, I think they asked some permission or something. I said, yeah, yeah, definitely. So it was at
Sir,
least.
we were only given question papers for last semester's ensigns. With no other question papers we have received.
Oh, I see. Okay, that's a good thing actually, because you know what happened in our time. There was universities had this last 10-year question paper released every year. It used to be available in all these book vendors, and some people used to just mug that. And the good thing is that by mugging that, you can get quite a bit, and then you don't learn anything basically. Okay. But then when you are told to not do that, so then you have to design the question paper in a way that, like when you are told that you will be given that question paper, so then you have to design the question paper in a way that it is not repetitive. And we didn't have the advantage when I was giving my BSc exam, because that year the syllabus changed. So not fully, partly, and lot of questions were not repeated from anywhere else. But that's what I think helped me a lot. Like I actually learned. So some people can get away with that. So I do not entirely endorse this practice, but I do not have a strong reason to not say no either. So let it be. If I don't give, if institute doesn't give, you can get it from your seniors, right? So there is no point of stopping it, right? The only point is for us to make a question paper which is not resembles anything of past year, but that makes it hard. That's the other problem. Anyways, so let us. Anyway, so I don't worry too much about exams, because this is a advanced course, and in advanced courses there can be only two type of question paper. One is too hard, one is too easy, and I will not make too hard, because that will be like, that will come back on me. It will make me upset, and I'll think, what have I done all this time. So the question paper will be mostly easy. 70-80% will be easy, which is very easy to score if you have paid attention. And generally also, like as I told earlier also, that I don't like failing anybody. It's like, because it comes back to me. I have to set the repeat exam and all that. So don't fail, and which means follow the basic course, basic material. Like it requires lot of exceptional effort to fail in my courses, at least, because some questions are straightforward from, and you have to be completely blind to that, completely ignorant. And I hope none of you are like that. So, and so don't worry too much about the difficulty level and all. If you have followed the course material roughly at some decent level, and have a command on the assignment problems, then there is no reason to do bad in exam. In fact, you can score full marks. And also, as I told you, some of you, at least as I will say, all of you should submit the exam, should submit the assignment papers as you are solving it. The only reason I'm asking for this is that I need to know that how you are doing with those problems. Earlier years, I had a gauge of how people are doing, how much they have understood. This time I am clueless, and that's why when Last time also when I was setting the quiz paper, I first set a paper and then I thought, what if they cannot do it? Because we don't know. I don't know how much you have done. So then I made the question paper easier. So this whole thing makes your, I don't know, yesterday if you are hearing that director was saying the brand value of ISAR, right? So the brand value means that you can handle a difficult question paper or somewhat a decent paper that others are handling, like ISAR Pune or IISc, right? So that should be, there should be some quality in the question paper. It cannot be arbitrarily easy. Okay, so what we'll start with today is we'll continue on the last time's statements that we said that quantum mechanics of many identical particles, and let me quickly summarize that what we learned and give a trailer of what are we going to do today, and then we will discuss the details. So the first point we said, so let's say I have a Schrodinger equation of many identical particles minus h cut square by 2m del 2 del ri 2 plus v ri plus v2 ri rj plus v3, and of course I have to put the carefully put the summations. If you put the summations,
Sir, whatever you're writing is very blurry. It's not properly visible. I guess
is
it's
it
your
a focus issue? Is it light issue or focus issue? Should you, yeah, turn on
Sir, actually, it's not a focus issue. It's like board is not clear.
okay, so we'll move, take the curtains. Let's see if more
Yeah,
light helps.
like the white chalk is like barely visible. It's like that.
Okay, should I use a different color then?
No, white is fine. I mean, maybe closing the curtain or something would work. Maybe.
Okay, see how it is now.
Huh?
How is it
It's
now?
same only.
Okay, so then what's the solution? Light.
No, now no, this is too much light. It's not at all. This one is fine, sir. We'll do something.
So how it is now? How is it looking in this screen?
Hmm? Sir, it's like if you reduce brightness, then I guess it will be more visible.
So is again writing big is the solution?
No, no, no. Reduce brightness, I said.
How can I reduce brightness? I mean,
Yeah.
okay, it is not like ITV. Okay, how about this? How is it now? How is it now? We
Sir,
have
sir, IT guy is here. He's tackling the issue. You can continue.
okay. So wait, yeah. So it is a problem is we have a discrete set of operation, right? And discrete set of operation means we can either turn on a light or turn it off. There is no continuous in between state. So that then within this set of operations, what can we do to make the screen better? That is the question.
Sir, you
So,
can just write on your tablet and that should be better.
okay, I didn't bring the tablet. Okay, I have to go back and bring it. That will waste a lot of time again.
No, 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 not needed.
Okay.
Maybe next time.
Okay, maybe next time onwards I'll write. But today's class is also important. So no, but how then I have to move the camera. That is a very big thing to do because you have to know after you move the camera if you can focus it or not. If you cannot focus it, then or you have to call the IT guy. Okay.
IT guy is here.
So what is he saying? What is the reason? I mean, what can we do?
Sir, you can continue. He's tackling the issue.
Yeah,
It's
so
all
they
right.
are saying there is some problem that this screen is not visible properly. Can you see what's the? I mean, we don't know the reason. That's
Yeah,
the problem.
now it's better actually.
It's better. What, oh, he did something. What
Huh?
did you do?
I mean,
He
if
did.
you'll write a bit darker, then it would work.
Okay, it's that simple. Okay, ISO means literally increasing the resolution. Okay, great. So just increase the highest, but
Yes.
highest ISO means also, uh, yeah. How about now?
Sir, it's all right. If you'll just write a little bit darker, that will work. That's it.
Okay, I will try. Okay, so this was the Hamiltonian we started with, and we said that okay, that the permutation symmetry of this Hamiltonian implies that there are certain restrictions on the allowed symmetry of many particle wave function. Okay. This was the point we realized. Although there are many ways to satisfy this equation, how about now? How is it now? Is it better? Can you hear me?
Yes, sir. It's fine now.
Oh, very good. Okay, I think the ISO is the solution, and that is something you can control almost continuously, if not entirely continuously. Okay, so this was the first thing. The second thing we learned is the symmetrization postulate. And the point of the symmetrization postulate is, so there exist only bosons and fermions in 3D. Okay. This point is important. Textbooks don't say that. Sometimes, not always. They just said, okay, there is only boson and fermion. Okay. But this is the main point, and bosons are those which are n particle wave function okay, that is fully symmetric, and fermions are those that is fully antisymmetric. Okay, so this is what we learned, and we also, so this is what we learned so far. Now what we will learn today, so let me just give an quick outline, that if I ignore the V2 and V3, which means I just want to describe the many particle wave function of a bunch of particles which doesn't have any interaction. That's what we will learn. So then how will they look like according to symmetrization postulate? So that is what we will learn, and what we will see is that the bosons will look like this. So the general one, which is an allowed wave function but not a wave function according to symmetrization postulate. So let me remind that by writing it is not by symmetrization, will look like this. If these phi's are the single particle wave function. So if I say there are n particles in a particle in a box potential, right? Particle in a box is this potential, this much. These two are not there. So then those n particles will have their own single particle wave function. So these phi's are those single particle wave functions. Okay? So they will look like phi L1 R1, phi L2 R2, and so on, phi Ln Ra. So this is how it will look like, general, which is not the symmetrization postulate, but symmetrization one will look like this, which I will show how it is exactly. This psi, and the way to describe it will be NKS. NK is the occupation number of the kth level. So it is like saying, so let's say I have a particle in a box, and I put particles here. So put one here, two here, one here, one here, one here, one here, one here, like that. So they have some NK, right? NK is the number of particles in that level. This is two here, one here, three here, one here, right? Like that. So this is that NK. So we will show that it is only this NK that matters. That is the only information you need, and that will lead to this Fock space formalism, which is describing a many-body wave function in terms of this NK alone. Okay. So psi ks will look like this: n1 factorial, the number of particles in that, times factorial, n2 factorial, n infinity factorial, whatever it is, divided by n factorial. N is total number, and P is sum of all the symmetric permutation. So you will see this will be written as as a symmetric permutation. We'll show exactly how to write it down. And for fermions, it is same, except this factor is just 1 by n factorial, and everything, then there is this sum p, but it is antisymmetric combination. So this is what we'll learn today, and then we will learn that each of these wave function corresponds to an unique nk, correspond to, and this is for boson, this is for fermion, and there is a unique way to describe this only by the nk, and that is your Fock space. So this is the fourth topic, that is Fock space. Yeah. This is everything what we will cover today. So let's start by a little bit of revision on the last statement that I made today, which is just more like a trailer for quantum field theory, but rather I will not go in the depth of that. Why do I need that? So if you remember last time I talked about, so everything is clear on this board so far, right? Okay. So last time we made a brief statement, so let me elaborate a little bit on that, because some of you asked me some questions about it. Is that how this notion of non-locality and quantum field appears naturally? Right? So we discussed that in the symmetrization postulate, if I have a electron, if I am working with two electrons, if one person is doing an experiment in the permanent campus and another person is doing an experiment in temporary campus, so there are two electrons. One is permanent campus, one is temporary campus. And they can be anywhere. One is here, another is in Andromeda galaxy or something, any two places. So then their wave function will be Pt plus Tp, plus minus whatever, or something. Yeah, so plus or minus according to symmetrization. Right? So that means that if I do take any two such electron, they are automatically correlated, right? They are entangled and non-local. So if I perform an experiment here in the permanent campus and found my electron to have some property, let's say some any property, then it collapses to this state, right? So that means by performing an experiment in the permanent campus, I collapse this state of that electron, right? So that means everything is already non-local. The electron states are already non-local. So this idea, the way to handle this idea is by quantum field theory. So that tells you there is, so as we know, there particles are basically a lump of matter, a lump of energy in the space-time, right? So the quantum field theory point of view is there is no particle, there is only field. So there is only one electric field that is everywhere, and that field has excitation. So these excitations are these particles. So that naturally incorporates this idea of fields, and that says that all particles are all these identical particles are basically one field, and the particle that lump you are working with is an excitation of that field. Okay, and then you might ask, then this field can exist. So then you might think that this field can exist even if there is no physical particle, there is no physical excitation, there is no excitation. So then the field is still there. So that is like the vacuum of the field, and the vacuum need not to be an actual vacuum. That is what we will learn in the later part of this course, which is relativistic quantum mechanics. We will learn that the vacuum is a many particle automatically. A vacuum is an infinite particle state automatically, and then an excitation is taking one particle from that infinite particle state to a higher energy. Right? That is what the particles are, and we will see that this is a very strange idea when you think like that, but you have actually seen this idea in action elsewhere. you have learned about this concept of particle and whole, right? In when you learned about semiconductors, right? So this is exactly that idea, except there it is easy to imagine that what is a particle and what is a whole is the absence of a particle and particle is a particle. But here you have to imagine harder because you have to think the vacuum is like infinite particles and excitation is a particle and absence of a particle is antiparticle. Right? So this is what we will learn eventually. So this is how quantum field theory enters through this a natural description of many particles physics, and we will not discuss it any further in this context, but we will come back to it a little bit in quantum in the later part of the course if I ever reach there because I am going slower. That is in relativistic quantum mechanics, and properly we will discuss it in quantum field theory. Okay. This is a very strange idea, but this idea is the most powerful idea of modern physics, and it's so powerful that using this idea in quantum field theory, the calculation you can do, they are verified up to 16 places after decimal. So this is the most powerful theory of physics, or like you can say, like most strongly verified theory. Okay. So now let's look for quantum mechanics of n particles in the solution of Schrodinger equation. Now you might ask that how do I construct? So what do I start with? I start with the single particle, right? H cut square by 2m del 2 LRI2 square plus V Ri phi n Ri En phi n Ri. This is what you have learned. This is what you have solved throughout quantum mechanics 1. Right? Particle in a box, harmonic oscillator, hydrogen atom, all these problems, single particle problems. Okay. Now I say that I have such a system which is just a single potential which is equally seen by all the particle, no interaction potential. You might ask, oh, hydrogen atom is the interaction, but you remember that we have ruled out this the interacting structure by saying the nucleus is too heavy, as if it's like some frozen object which makes this field, and in that field the electron experiences the potential. Right? So it's a two-body problem which you have converted into one-body problem by saying the electron doesn't, the nucleus doesn't move because it is too heavy. This is called Born-Oppenheimer approximation, and this is not always true for certain systems. Then you cannot do this. Okay. So this is the structure of the problem we learned, and we want to ask the question: if I have, so this is this n, these levels. Is a level of single particle state. Now there can be many levels, by the way, as you know, but I am just writing one number. There can be n, l, m, and ms, right? M, n, l, m, z, and ms. There are four. It can be 4 numbers. It need not be one number. But let's say it's one number. Okay. So now I want to ask the question: what is the general solution of this equation? For n particle, same equation, but now I have n particle. I am not yet writing what is that n, what is this e, but let's say some e. Okay. I am not, let not also put this. Okay, so this is my full solution. How do I construct this solution with this, right? If I just say I have a particle in a box, this is my system. This is my system with this kind. These are the energy levels in single particle. Now, if I put many particles into it, how will the wave function look like? So generally, an allowed wave function is this, which is easy to see why it is allowed. Is this. The simplest allowed wave function. So let's say there are n levels and n particles. So each of them will go to some level. So let's say particle 1 is going to the level 2. So then L1 will be 2. Particle 2 going to level 4. So L2 will be 4, like that. So each particle has a level, right, where it is going, where I am putting it. And this is the most general one, because of course you can see if I put it here, this will act, a particular Ri will only act on that part, and then the rest will be just intact, right? So this is the most general allowed solution. Okay, so let's see. We can also see some very simple examples that. So
So
as I
the
said,
second
yes,
Schrodinger equation you wrote, it's for a multi-particle system.
yes.
But
This one is for one particle. That's why I say this label is for single particle state, and this is for n particles.
but sir, there's only one kinetic energy term, one uh, one.
Very good. Thank you for looking at it. Right? Okay. Is it all clear now?
Okay, so fine.
Okay. So I can say, okay, three particle going to this, right? So then it will be phi 1 R1, phi 1 R2, phi 1 R3. Or I can say, okay, one is going here, another is going at 1, 2, 3, another is going at somewhere 7. Let's say then phi 1 R1, phi 3 R2, phi 7 R3, right? Like that. And you can always see that this, if I write down the full thing, so del 2 del R1 square plus del 2 del R2 square plus del 2 del R3 square plus V R1 plus V R2 plus V R3, which is identical for all of them. If it acts on this, it will give me only that energy, right? And that way whole wave function will remain intact. Okay. So now I want to ask the question, then what is the total energy of this system? Can somebody tell me that? What is the total energy of this system? Sum of all these, right? So in this case, it will be 3 times E1. First case. The second case will be E1 plus E3 plus E7. Okay, and so on. So generally the total energy will be is, am I going out of the range? Probably. So the total energy will be each of this level. Okay. Now there is, you can see there is a simpler way to write down the total energy. That is just to write E as NKEK, which means instead of summing all the energies, you multiply the energy of that level times the occupancy of that level, right? So in this case, this is just 3, instead of, this means here you write E1 plus E1 plus E1 in the first case. Here you will just write 3E1, right? 3 is the occupancy of that level. Okay. So these are the two ways to handle it, right? So then how many ways you can do that if they are symmetric particles? Now comes the question of, I have not used any symmetry so far. I just assumed as if they are completely different particles, right? I have not used any symmetrization argument. Now when the symmetrization arguments comes, then you might say, when they are all identical, so then if R1 goes to L2 and R2 goes to and R2 goes to L1, there is no difference, right? They are all same. Right? So then how do I take into account for that? So that means this configuration is also perfectly legal. L2, R1, phi L1, R2, and so on. And all possible such pair shuffle, right? All of them are equivalent. Yeah? So then how do I take care of that? So let's do some counting. Okay. So just remember this, that my general psi is given by a particular Li and a Ri, particular set of Li, and this is L1 R1, and this configuration implies this. But if you jumble them, that's also a good wave function, right? Equally good because they are all symmetric. And the total energy is given by NKEK, occupancy of the kth level, right? Everybody in the same page with this? Okay? Is it all clear? Yes, no?
Yes, sir.
Okay, very good. So now we want to ask the question, how many such ways are there, right? I said there are different ways. So that number is very simple to calculate. You just ask how many ways you can put N1 particle in the first level, right? So what is that number? How many ways you can put N1 particle in the first level? Huh? Don't mumble. Say it more loudly. N? Remember, I have N particles and I have these levels 1, 2, 3, 4, 5. I am asking how many ways you can put N1 particle in level 1. So their occupancy level is N1, N2, N3, like that, something like that. Okay? So how many ways you can put N1 particle in level 1?
And choose N1 factorial.
Yeah. Okay, what did you say after that? You would first. Okay, I hope you didn't try to overdo anything and choose N1, right? Right. So after that, how many ways you can put the N2 particle in the second level? Huh. N minus N1, choose N2, right? And so on, right? So now what is the total number is a product of all this, right? So if you take the product, what you will get is this. So the total number ways to do that, this is just a elementary division of combinatorics, and ideally I am supposed to write down this answer directly. All these wi's, product them, and this is n factorial. There may be infinity levels. Okay. Okay. So now what? So now let us say, now what does this mean? What does symmetrization postulate tells you? So first thing is that there is a degeneracy, right? All this level, all this number of ways you can put, because the configuration, the total energy only depends on these numbers, right? It doesn't depend on how you orient them, right? Because they are symmetric, right? So that means all these states, this many number of states has the same energy, right? Same total energy, right? Because they all correspond to this configuration nk. Everybody got this point? Okay. So that means,
Sir, can you repeat this last point?
yes. So what did we understand? That there are this many ways to put N1 particle in level 1, N2 particle in level 2, N3 particle in level 3, right? This many ways to do that, right? So then the question is, if that is the case, okay, if that is the case, then what is the total energy of that system? The total energy is always sum of nk ek, right? So let us say I take that, I put two particle here, one particle here, one particle here, and two particle here, right? Now, how many ways, how many particles I have? 1, 2, 3, 4, 5, 6, 6 particles, right? So out of 6, I can put 2 here. So then the number is 6 factorial by 2 factorial by 1 factorial, 1 factorial, 2 factorial, right? This is the number by this formula. So there are this many configurations. They are all identical particles, 6 particles are identical. How I can put them there? There are this many configurations. And what is the energy of each of these configuration? Each of these configurations energy is 2 times E0. This is 0, let's say. Okay, let me call it 1 instead of 0. 2 times E1 plus 1 times E2 plus 1 times E3 plus 2 times E4, right? This is the total energy of this configuration, right? Now, this many configurations have the same energy. Do you understand this point? Online audience?
Yes, sir.
Okay. So that means there is a degeneracy, right? These many configuration have the exactly same energy. That means there is a degeneracy, right? So now comes the important, interesting point. So, did any of you learn about entropy in statistical mechanics course?
We were
Yes, sir.
entropy
Sir,
in
in thermodynamics part. Yeah,
You
yeah.
have learned about entropy?
Yes, sir.
Okay, did you learn about what is the difference between entropy of a gas of distinguishable particle and a gas of indistinguishable particle, the Gibbs entropy?
No, no, sir. We only studied in like thermodynamics part or entropy of gases and stuff.
Okay, so then I will not go into that. But the point is this that this was actually first demonstrated by Gibbs, because so this is a very interesting fact. The people somehow knew about quantum mechanics, some quantum mechanical aspect, even long before the birth of quantum mechanics, because they suspected some aspects of this symmetrization. Okay, so some aspects of this. So what was the point? The point was all these things we are saying at an abstract level, right? We said there is a symmetrization postulate that tells you that this many wave functions, okay, there are this many wave functions. So according to the symmetrization postulate, these many wave functions have the same energy, right? But how do I know? It's a statement in some configuration space of Hilbert space, how things are arranged and like that. How do I experimentally verify this? Okay. So the way to think about this, if you calculate the Gibbs entropy of this, so entropy is sum over I pi minus log pi. Okay. So you can show. So I am just making a statement. You think about it when you learn it. Okay. That the entropy will be completely defined to these cases. Okay. If there is no symmetrization postulate, then there are that many states, right? Then there are that many states of different. Then they need not be degenerate. Right? Okay. So let me just make this claim. Okay, so what does symmetrization postulate means? Let me clarify this. So symmetrization postulate says there will be only one state corresponding to these states, right? Only one state. Let me note that right. There is only one state. Okay, and that one state is the symmetric combination of all these states, right? Everybody got this point? So these states could be written like this. So phi 2 R1, sorry, phi 1 R1. There are two particles here, right? So two particles, if I write it in terms of these two particles, this whole state, I will rewrite it as particle 1 went to level 1, particle 2 went to level 2, particle 3 went to level 2, particle 4 went to level 3, particle 5 went to level 4, and particle 6 went to level 4, right? This will be the state. That is how I will write this same state instead of calling it in terms of number. So notice this thing. So if you have not understood it, let me clarify it once more carefully. Okay. So what is symmetrization postulate doing and what does it mean with this example? So let us say I have 6 particles, okay? 6 particles are labeled as 1, 2, 3, 4, 5, 6. Okay? I will later say they are indistinguishable. Right now, let's say this is the scenario. And there are these levels. And I told you a picture that I can describe these particles by saying 2 went here, 1 went here, 1 went here, 2 went here. So these levels are E1, E2, E3, E4. Okay. So how can I describe this scenario? I can say that the first particle went to level E1, right? So that means first particle is at level E1. The second particle is also at level E1. So I write it as this. If you want to remember, you can put a small tag below. The third particle went to level 2. So 2. Okay. Then the fourth particle went to level 4. Level 3. And the fifth particle went to level 4. 4, 4. 6 also 4. Right? So this is one way to describe this state. Right? The other way is this. Nk. It just said 2 particle in level 1, 1 particle in level 2, 1 particle in level 3, another particle is level 4, right? Now the point is these two are completely equivalent because of symmetrization. Why? Because it doesn't matter whether first particle went here or the third particle went here, right? They are all equivalent states, right? So this configuration will have wave function this, phi 1 R1. So instead of R1 I am writing just 1. Phi 2, sorry, phi 1 R2. Let me write R1, R2, otherwise you will be confused. R1, R2. The third particle, phi 3, R3. No, phi 2, R3. Phi 4, phi 3, R4, phi 5, no, phi 4, R5, phi 4, R6, right? This is the meaning of this. This is a shorthand of that. Okay. Now this is the symmetrization postulate tells you all such symmetric combinations. The wave function is a linear combination of all such symmetric combinations. So what is the another symmetric combination? Another is just take this phi 1. Let me just shuffle them, right? So I can say that phi R1, R2, R3, R4, R5, R6, right? So now I can shuffle them. I can put the 1 here, 2 here, 3 here, 4 here, and 4 here, right? This is also equally good thing, right? I can write another such thing, right? Another such. All of them has to be added, and they all correspond to the same state, right? They all correspond to. That is what symmetrization postulate tell you, right? So in one way you have, and there are how many such states? There are 6 factorial by 2 factorial by 1 factorial, 1 factorial, 2 factorial. This many states, right? So that what is that number? So 6 factorial divided by 2 factorial will be 6, 4, 3, 2 factorial goes away there, and 2 goes away there. So 6 into 2, 6 into 3 is 18 into 2, 36 states. So there will be such 36 combinations, right? So there are 36 states like this whose symmetric combination is this state. Right? So symmetrization postulate tells you there is actually only one state, which need not be symmetric also, it could be anti-symmetric, but there are only one state corresponding to this 36 states. Let's say these are boson, so they are all symmetric states. Right?
Sir,
Everybody got this point?
uh, I have one
Sorry?
question. Uh,
Yes.
Sorry.
in last class, you wrote the symmetrization postulate. You said the wave function of n identical particles is either fully symmetric or fully anti-symmetric.
Yes.
How does it come up to here that all these states are the same state or something?
Yeah, so that is what I said, right? Earlier, if you remember, there are two particles, 1 and 2. It can either go here or go here, L or R, right? So your state is L1, R2 plus, let's say symmetric, right? Not anti-symmetric. Let's assume it's symmetric. Or it can be R1, L2, right? So the wave function, if according to symmetrization postulate, is this, right?
Okay.
Not these two,
Sir,
not these two, but instead of this one, right? These two are not allowed wave functions. This is the allowed wave function according to symmetrization postulate, right?
Okay.
So instead of 2, now you have 1. So degeneracy reduced from 2 to 1, right? So this is same here. Instead of 36, you have only 1, which is the symmetric combination of these 36, right?
Okay.
So this is the point.
Sir,
So yeah,
This
so there will
another
be
5,
180, right?
6
Not
factorial.
36.
It's 6
sorry,
times
did I do a
5.
mistake in this?
Yes, sir. Into 5 would.
So 6
No,
factorial
this
is
is the
6
number.
times 5 times 4
Yes,
times.
sir.
You just wrote 6 times 4.
Oh, okay, okay, good. 6, 5, 4, 3, right? 2, 1. So 2 is gone. So this 2 will make it 2. So how many it is? 6 into 5 is 30.
180.
180. So there are 180 combinations. So there will be 180 such combinations. Instead of there it was 2 to 1, there are 180 combinations are there. So these 180 states are basically one state.
It's
This is the only
90.
allowed
There's
state.
another
Now
2
this,
down there. So you have to cancel that.
sorry, say
Oh,
that
no, no,
again.
no.
I
It's
didn't
fine. I
follow.
guess. It's fine. It's fine. It's fine.
I am assuming symmetric
It's fine.
combination. Okay. So if I could have assumed antisymmetric, but I am not entering in that complication. Let us say these are bosons. Okay. So that now,
Sir,
yes,
one state is a function of all small states. That's what.
yes, yes, and that is the only state nature allows, right? That is symmetrization postulate.
That is for
Bosons, yeah. For fermions, you will take all such combination, which each pair combination will give you a minus sign. I'll show you how to write down the fermion. Okay. Then the point is, now this abstract statement, how do you verify it in an experiment? Okay. So the way to verify is you can calculate the entropy of this system. Okay, that you will learn when you learn about entropy. I will not go over it. You will learn it in StatMech. So this was something that Boltzmann, not Boltzmann, I think Gibbs. So Gibbs
Sir,
figured out. Yeah.
so the one that we have written, like instead of 180, there will be just one state, which will be the symmetric one. So similarly, there will be the anti-symmetric part. So that is
Yeah. That is also another possibility, right? But if it is so, there are two possibilities: either symmetric or anti-symmetric. I am assuming if it is one of these, the other will not happen, right? So bosons cannot be fermions and fermion cannot be boson. So there are two possibilities: either symmetric or anti-symmetric. You could have chosen any one. Here I am choosing the symmetric. Right? So these particles, if they are, let's say, imagine some known boson, right, photons or something. So then they will not behave like electrons, right? So they are either, so it's a character already assigned to the particles, right? Do you understand this point?
yes, sir.
Yeah, it is like saying all the footballs in the world and all the cricket balls in the world, right? So there are two categories of objects. Right? Okay, so now let us say, okay, so now we want to ask this question: how do I experimentally verify this? So you can show that if you have a gas of distinguishable particle, their entropy will be something, and if you have a gas of indistinguishable particle, their entropy will be completely different. Especially if you have this degeneracy, which means there is only one state, not that many states. So this, how many objects, how many probabilities you will count, that will change. So that's a experimentally, entropy leads to experimentally detectable quantities, right? So that's the connection between this and real world detection. Okay, so that is how one can show that this is correct, right? And these experiments were done. And what is interesting, that it was Gibbs who figured out long ago that some notion of indistinguishability is required. But he didn't think in terms of quantum mechanics, he thought in terms of identical gas of particles. Okay? But this is interesting to show that an experiment could have also figured it out separately, that you have this notion of indistinguishability or symmetrization postulate that doesn't fit within the classical picture. Okay. Okay, so now we will show how to exactly write it down for any problem, any such set. Okay, so first let's talk about the bosons. As bosons I have already written down, but I am just showing the systematic way to do that. Okay. So the systematic way to write down. So let's say now I establish that if I specify the nk, I specify the full wave function, right? So this nk for symmetric will be sum of some normalization constant, sum of all the permutation, and those permutations are given by phi L1 R1, phi L2 R2, and phi Ln Rn. Right? So now I want to figure out what is this C, and that C will be phi S nk. They have to be normalized, has to be 1, right? And this means this has to be C square P, this whole object, P prime, this whole object. Now they are all orthonormal wave functions, right? Each of them are orthonormal wave functions. So then it will be simply the sum of such terms, right? So this will be.
Sir, what is P here?
P is the permutation. How many permutations are there?
Okay.
Each P, every time you act P, you shuffle one pair. Okay. This is what I am using from the beginning, by the way. So this is the sum is over all such P and P prime. Okay. So then the only combination that will satisfy this is C square sum of P P and P. I'm just writing P here. Okay. Not writing this whole thing. So that means it is just C square times number of permutations. So what is that number? We just derived that number. That number is nothing but n factorial divided by n infinity factorial. Okay. So that means this has to be equal to 1, right? So that means C has to be equal to okay. So now my whole wave function will be is it visible or going out of board? Okay, from where it is going out of board?
So it's till sigma p it is visible.
Okay. Times P right? This will be my full wave function. So let's give an example. Okay. So let us say I have this case that let's take this example 210. This is my occupation number. This is my NK. Let's say it's particle in a box. 2 particle in ground state, one particle in fast excited state, and so on. Right? So how do I write this? This will be phi 1 R1. This is all the symmetric combination we have to write, right? Phi 1 R2, phi 2 R3, right? Then pair shuffle. This pair shuffle will give you nothing. So this pair shuffle, phi 1 R1, phi 2 R2, phi 1 R3, right? Then another pair shuffle will give you phi. So here I shuffled these two, right? Now I can shuffle these two. So this phi 2 R1, phi 1 R2, phi 1 R3, right? And according to this number will be 2 factorial divided by 6 factorial, that is 1 by root 3, right? So this will be my full wave function. Okay. So now it turns out there is a very nice way of writing it, that is called permanent. And okay, I will come to the permanent, but first let me write down the anti-symmetric case. So now I want to do the same. Everybody understood this point, right? The symmetric wave function fully. Okay. So now I just want to write down what will be it for the if they are anti-symmetric, then what will happen. Okay. So if these wave functions are anti-symmetric, so then you have to write psi in k a c minus 1 to the power p, because each permutation, each pair shuffle will give you a minus sign, right? So then phi L1 R1, phi L2 R2, phi Ln L infinity actually. So let me write Ln, because I am writing it in this form, right? Okay. Now notice one thing will immediately happen. You can never have more than one particle in one state. Okay. And if you do, such a state will always give you 0. Okay. How do I know that? How do you show that? Can somebody tell me that why it should happen? The question is, I can never have a configuration like this. Any configuration where the nk, the only allowed values of nks are 0 or 1. You cannot have 2. Okay. If you have 2, such a wave function will always vanish. Can you see that simply? How? Right. So there is a very simpler way to see that. So how do I write this wave function, this thing, in this case? Okay. So this thing is called using determinant. Okay. The simple way is using determinant. So why determinant? Because, so let us say, let's take this example. Let's take something simple. Let's say 1 1 1. No, 2 1 0. Let me allow this 1 1 1 0 0. Okay. So then how should I write this combination? I can write this as 1 1 1 0 0. Let's say the symmetric or anti-symmetric, whatever. So some normalization which I am not writing yet. I can write it phi 1 R1, phi 2 R1, phi 3 R1, or let me write phi 1 1 R1 R2 R3. Okay. Now phi 1, phi 2 R1, phi 2 R2, phi 2 R3, phi 3 R1, phi 3 R2, phi 3 R3. Okay. Now notice this determinant will automatically do this job. Why? Because I can write this wave function, expand this as phi 1 R1. First term will be phi 2 R2, phi 3 R3. Now automatically the shuffle will pick up a minus sign, right? Minus phi 2 R3, phi 3 R2, right? Automatically it will pick up a minus sign. Similarly, you can write down the other two rows, phi 1 R2 and so on, right? And you can just write it down. Okay. Now you can immediately see if two of them are same, right? That means this 3, let's say this is 2 for this case, and this is 1. If a determinant have two identical rows, that determinant vanishes. You can just expand it and show it very easily. So that means there is no way, if it is anti-symmetric, you can have this configuration. So this is Pauli exclusion principle that comes naturally from the symmetrization postulate. Okay, for the anti-symmetric wave function. Now notice you can also write this thing. Instead of putting a minus sign, if you put plus sign, you will get that. So these things are called permanents. So determinant without a minus sign is called permanent. Right? So if I write the wave functions in a form of this, take determinant, you get the anti-symmetric, take permanent, you get the symmetric. Now show this, I leave it as a homework, it's very trivial. Show this C is 1 by n factorial, root 1 by n factorial. There is no n1, n2. Why? It's very easy, it is either 0 or 1. Right? So there has to be. Right? So then you can construct, if I give you any problem like that I give you, let's say I give you a configuration 2100 or any configuration in any ways, you can always write down the many-body wave function for that if you know the single particle wave function. Let's say particle in a box, harmonic oscillator, whatever. Right? So that is all I wanted to tell you today. Okay. Next I will talk about Fock space. That how do I manipulate? So this is also very interesting. So now I am telling you. So this is a little bit of trailer for the next day. It's very exciting, and I want you to get head start with thinking it. So now I can completely describe a state in this, right? This is enough, right? So it turns out the way to build a Fock space is by saying, let's say there is no particle. Right? So then it is 0, 0, 0, 0, like that, right? No particle, nowhere. Then you put one particle somewhere. Then it is 0, 0, 0, 0. It could be 0, 0, 0, 1, like that. Then two particles, right? So it could be 1, 0, 0, 0, 1, or it could be 1, 0, 0, 1, 0, 0, 0, 1. Now it could be also this, but this state is not allowed for fermions. Right? So you can construct this two. So now this is, you can think each of these point as a point in some high dimensional graph. And now we want to ask how this graph, how these points are connected, and what are the allowed graphs you can construct in that. Given that in one case this kind of point vertices are not allowed in that graph. So this is an alternative way to think about a many particle problem as a graph. Okay? I will discuss more about it, and some of you can take it as a term paper. If you see last year's term paper, Rohit used that idea and visualized a problem of, so now you will see, you will learn this kind of things. So let's say I have some process that takes you from this state to this state. So let's imagine this process. Okay? Let's say there is a lattice and a particle hops from here to here. So this state is 0 0 1 0 0 0, and this hopping is 0 0 0 1 0 0. Right? This is the process. So now you can imagine this hopping process as a process in this different graph in this high dimensional space. Right? Now this problem looks trivial because it's just one particle, but it could be more particle. Right? It could be this also. 1 1 1 0 0 0, 3 particles. Now the processes are like this. So now this cannot hop here if it is fermion, but if it is boson, it can hop here, right? So if it is boson, then it is 1 2 1 0 0, or it can be 1 1 0 1 0 0, right? These are the two possible states it can go if it is a boson. So if this point is this, it can go here and here. Let's say two other points, right? But if it is fermion, only this is allowed. So if it is fermion, it can only go like this. Yeah. What? Oh yeah, you are correct. Right. So this is an alternative way to visualize a many body problem, a many body dynamical problem as a high dimensional graph problem. Okay, and that leads to many insights. Earlier I told you about this many body localization. So you can show that in real space, if the electron may or may not be allowed to go one place to another, depending on the Hamiltonian, depending on the process. And in the Hilbert space, it can have different behavior. So many body localization means something. So let's say I have this complicated high dimensional graph. Usually this is the vertex, this is my 0, or if I have a finite number of particles, it can have some graph in high dimensional space. So you can show there are Hamiltonians which keeps the particle confined in a finite region of this high dimensional graph. So those are NBLs. Okay, and there are very interesting scenarios called non-ergodic metals. What happens there? That it's a metal. Metal means the electron can go from here to here. They are spatially delocalized, right? But it can happen they are localized in Hilbert space. So these are very interesting examples. Nobody found yet a ergodic insulator, and that is something we are trying to find, but nobody knows about it yet. But there are very exotic kind of states. So you expect now then there are two kind of questions. If something is localized in real space, does it mean it's also localized in this high dimensional graph or not? Right? This is the question. And this leads to this question of ergodicity breaking. Again, you will learn ergodicity in StatMech. You will learn that ergodicity is a very important hypothesis that we need that StatMech to work. But there are kind of examples like this, which is basically destructive interference. That there is a many body destructive interference that says this probability amplitude is 0 to find it here. So that's why it is stuck here, right? So and they are very interesting for many other applications like computing and topological quantum computing and all, where you can guarantee that your state, whatever is your dynamics under that Hamiltonian, the state is stuck there. It's not going to go anywhere else, right? If you can guarantee that, then you can do a lot of things with that. So these are very interesting extensions. We'll talk about this little more later, but you can take it as a term paper. Okay, so that's all I wanted to say for today. This is the main part in syllabus. Of course, those things are not in syllabus. Okay. Okay, questions, online audience, if anybody is there. Today you have also a lab. And many of you have to rush for 1:15 bus.
No.
Okay, so there is no reason to leave unless you are hungry, which is a very logical reason to leave. Okay, see you on Friday.